Picture a void so powerful, so utterly relentless, that not even light can escape its grasp. Now, travel back in time, before we knew these cosmic monsters existed, before their names filled textbooks and documentaries. Imagine the moment humanity first glimpsed the impossible, a black hole. It wasn't just a discovery, it was a revelation that shattered our understanding of the universe. For centuries, black holes lived only in the realm of theory, whispered about by mathematicians and dismissed as science fiction. But then, against all odds, we found one. And that discovery changed everything. What did that first black hole look like? How did scientists even begin to track down something invisible, something that devours stars and bends space itself? The hunt for it was like searching for a shadow in a pitch-black room, a puzzle wrapped in layers of cosmic mystery. Yet, through sheer ingenuity and the relentless pursuit of knowledge, we did it. This is the story of that breakthrough, a tale of curiosity, perseverance, and the sheer audacity of human imagination. It's a story that takes us from the chalkboards of Einstein's era to the cutting-edge telescopes that finally pulled back the curtain on one of space's darkest secrets. But here's what makes this journey even more thrilling. That first black hole wasn't just a scientific trophy. It was a gateway, proof that the universe is wilder, more violent, and more magnificent than we ever dared to dream. And as we peel back the layers of this discovery, you'll see how it rewrote the rules of physics, challenged our perceptions of reality, and opened doors to questions we're still trying to answer today. So buckle up, because we're about to dive into the heart of darkness, and what we find there might just leave you speechless. Think of space as a stretched rubber sheet, smooth and flat, until you drop a bowling ball onto it. That's the simplest way to picture how black holes warp the fabric of the universe. These cosmic anomalies aren't just objects. They're prisons of gravity so intense that once anything light, stars, even time itself crosses their boundary, there's no coming back. That boundary, scientists call it the event horizon, the point of no return. Picture it like a waterfall's edge. Once you're swept over, the current is too strong to fight. Inside, gravity doesn't just pull, it twists space and time until the rules of physics as we know them break down completely. What creates such a monstrous force? Imagine crushing the entire mass of a star 20 times heavier than our sun into a space smaller than a city. That kind of density bends the universe itself, creating a gravitational grip that nothing can escape. Even light, which zips through space at over 670 million miles an hour, gets yanked back like a rubber band snapping. That's why black holes appear invisible. They're cosmic vacuums swallowing every photon that dares to venture too close. But here's where it gets stranger. Black holes don't just trap matter, they stretch it. Imagine falling feet first toward one. The gravity at your toes would be so much stronger than at your head that you'd be pulled apart like taffy, a process scientists grimly call spaghettification. And time, near a black hole it crawls. A clock ticking on a spaceship near the event horizon would run unbearably slow compared to one back on Earth, a mind-bending effect predicted by Einstein's theory of relativity. Yet for all their destructive power, black holes are also cosmic architects. Their gravity sculpts galaxies, sparks star formation, and might even hold clues to how the universe began. They're not just destroyers, they're creators, shaping the cosmos in ways we're only beginning to understand. So while the idea of a black hole might seem terrifying, it's also a reminder. The universe thrives on extremes, balancing chaos and creation in ways that still leave us in awe. Long before telescopes could peer into the cosmic abyss, the idea of black holes existed purely in the realm of imagination. Back in 1783, an English clergyman named John Michell sketched out a thought so radical it bordered on heresy. What if there were stars out there with gravity so strong that even light couldn't escape? He called them dark stars, and while his calculations were rough by today's standards, the seed was planted. Picture this, a world still debating whether electricity was a parlor trick. Yet here was a man daring to suggest invisible monsters lurking in the heavens. The concept languished for over a century, dismissed as a mathematical curiosity, until Einstein rewrote the rules. His theory of general relativity in 1915 didn't just tweak Newton's gravity. It painted the universe as a flexible fabric where mass could bend space and time itself. Suddenly, Michell's dark stars didn't seem so far-fetched. Enter Karl Schwarzschild, a German physicist who, while serving on the front lines of World War I, scribbled equations in the trenches that described a point of infinite density, a singularity. His work hinted at objects so dense they'd vanish behind an inescapable barrier, what we now call the event horizon. Yet even Einstein balked at the idea. To him, these solutions were mathematical ghosts, too grotesque to exist in nature. It took decades for scientists like Subramanian Chandrasekhar and J. Robert Oppenheimer to prove otherwise. Chandrasekhar's calculations showed that dying stars above a certain mass couldn't stabilize as white dwarfs. They'd keep collapsing, possibly into something far stranger. Oppenheimer took it further, describing how a massive star's core might implode endlessly, crushing itself into oblivion. The irony, these theories were so ahead of their time that telescopes couldn't hope to verify them. For years, black holes remained a numbers game, a cosmic what-if scribbled in the margins of physics textbooks. But that all changed when the universe handed us a clue, not in the form of darkness, but in the brilliant fury of a dying star's last scream. The hunt was on. Karl Schwarzschild's mind was racing even as the world around him crumbled. In 1916, amid the chaos of the First World War, this German physicist was stationed on the Russian front, calculating artillery trajectories by day and rewriting the laws of gravity by night. Armed with Einstein's freshly published equations of general relativity, Schwarzschild did something extraordinary. He solved them, not just in a simplified, hypothetical scenario, but for a real, massive object in space. What emerged from his calculations was both elegant and terrifying, the first precise mathematical description of a black hole. His solution revealed a boundary now known as the Schwarzschild radius, a precise distance from the center of a massive object where gravity becomes so overpowering that escape becomes impossible. Picture it like a cosmic point of no return. For our Sun, this radius would be just under 2 miles. Squeeze the entire mass of the Sun into that tiny space, and its gravity would trap light itself. But here's what makes Schwarzschild's work so revolutionary. He wasn't just theorizing about some vague, dark star. He gave physicists an exact formula, a threshold where the known laws of physics simply stopped applying. Yet even Schwarzschild didn't grasp the full horror of his discovery. His solution described a perfectly static, non-rotating black hole, a simplified version of the spinning monsters we now know litter the cosmos. The singularity at its core, a point of infinite density, defied all logic. Space and time swapped roles there, turning the very fabric of reality into a one-way street toward destruction. Einstein, initially thrilled by Schwarzschild's work, grew uneasy as the implications sank in. Nature, he insisted, would never permit such monstrosities to exist. But the math didn't lie. Schwarzschild's equations showed that if you packed enough mass into a small enough volume, gravity would inevitably win, crushing matter beyond recognition. Tragically, Schwarzschild never lived to see his ideas tested. He died months later from an autoimmune disease contracted at the front. His breakthrough, however, outlasted him, laying the groundwork for a century of black hole research. It was the first hard evidence that the universe might hide places where reality itself came to an end. And though it would take decades for technology to catch up to his genius, Schwarzschild's radius became the yardstick by which we measure the unimaginable. Before we called them black holes, these cosmic enigmas had far less catchy names. Scientists initially referred to them as frozen stars, a technical term describing how time would appear to stop at the event horizon from an outsider's perspective. But that label didn't quite capture their terrifying allure. Then came physicist John Wheeler in 1967, who coined the phrase black hole during a lecture. It wasn't just a rebranding, it was a revelation. Picture the moment Wheeler, known for his flair for vivid language, cut through decades of sterile scientific jargon with two simple words that evoked both mystery and menace. The name stuck instantly, spreading through academic circles and popping up in headlines worldwide. Why did black hole resonate so deeply? Compare it to earlier terms like gravitationally completely collapsed object, a mouthful that even scientists struggled to say without stumbling. Frozen star sounded almost poetic, but it missed the mark, implying something static and cold rather than the voracious, space-warping monsters we now know them to be. Wheeler's term did something brilliant. It painted a picture. Black conveyed the absolute absence of light, while hole suggested an unfathomable depth, a cosmic trapdoor with no return. Suddenly, the public could grasp the concept not just as abstract math, but as a tangible if terrifying reality. The media latched onto the phrase, and soon, black holes seeped into culture, inspiring songs, movies, and metaphors. Sci-fi authors had dabbled with similar ideas before, but now they had an official, scientifically endorsed name to work with. Even critics who found the term too sensational had to admit its power. It turned an obscure theoretical curiosity into a household concept, fueling both scientific curiosity and pop culture fascination. Wheeler later joked that he wished he'd trademarked the name, but its true value wasn't financial, it was cultural. By giving these cosmic beasts the perfect name, he ensured they'd capture humanity's imagination for generations to come. Yet the term did more than just simplify, it shaped how we visualized black holes. Earlier descriptions framed them as oddities, mathematical outliers. Black hole made them feel inevitable, like nature's ultimate one-way streets. The name even influenced research directions as scientists began asking new questions. If it's a hole, what's on the other side? If it's black, how do we see it? Sometimes the right words don't just describe reality, they change how we perceive it. And in this case, two ordinary words open the universe a little wider for all of us. The cosmos loves a good tease, and Cygnus X-1 played its part perfectly. In 1964, as astronomers scanned the skies with primitive X-ray detectors strapped to rockets, they stumbled onto something bizarre, a flickering beacon in the constellation Cygnus, pumping out X-rays with such intensity that it defied all known explanations. Dubbed Cygnus X-1, this enigmatic object became astronomy's white whale, the first tantalizing hint that black holes might not just exist, they might be screaming their presence across the universe. X-rays themselves were the clue. In space, extreme violence usually means extreme energy, and nothing emits X-rays without a cosmic cataclysm. Cygnus X-1 wasn't just a faint blip. It was a rhythmic powerhouse, its emissions flaring and fading like a heartbeat. Scientists quickly realized they weren't looking at a star, or even a pair of stars, but at something far stranger. A binary system where a supergiant star 20 times the mass of our Sun was locked in a deadly dance with an unseen companion. And that companion, it weighed at least 8 solar masses, yet emitted no light at all. The math left only one grotesque possibility, a black hole gorging on its stellar partner. Here's how the horror show worked. The supergiant's outer atmosphere was being siphoned away by the black hole's gravity, spiraling into an accretion disk so hot it glowed in X-rays. Think of it like water circling a drain, but with temperatures reaching millions of degrees and matter moving at nearly light speed. Every flicker in those X-rays was a death rattle, a signal of gas being shredded and compressed before vanishing beyond the event horizon. By 71, the evidence was overwhelming. Stephen Hawking famously bet against it being a black hole, then conceded years later when the data left no room for doubt. But Cygnus X-1 wasn't just a discovery, it was a revolution. Before it, black holes were mathematical phantoms. After, they became inevitabilities. This was nature proving, in brutal high definition, that Einstein's nightmares were real and lurking in our cosmic backyard. The monster in Cygnus didn't just swallow light, it devoured skepticism, forcing even the most reluctant scientists to admit the universe was far stranger than we'd ever dreamed. The smoking gun for Cygnus X-1's identity came from watching its celestial waltz, a dance of death between a visible star and its invisible partner. Astronomers focused on HD 226868, the supergiant star at the system's heart, and noticed something bizarre. It wobbled, not randomly, but in a precise 10.5-day rhythm, as if tugged by an unseen hand. Calculations revealed the culprit had to be at least 8 times our sun's mass, yet emitted no light whatsoever. In space, that kind of invisible bulk only means one thing: a gravity prison with no exit. Then came the X-rays, the screams of matter in its death throes. As the supergiant's outer layers spiraled toward its dark companion, they didn't just vanish quietly. The gas accelerated to nearly light speed, heating up to millions of degrees and glowing violently in X-rays before crossing the event horizon. These weren't steady emissions either. They flickered hundreds of times per second, a staccato beat betraying the frantic churn of the accretion disk. Only an object with a black hole's crushing gravity could shred matter so efficiently and whip it into such extreme energies, but the final nail in the coffin. Jet streams, radio telescopes caught twin beams of particles shooting outward at nearly light speed, perpendicular to the disk, a classic black hole signature. Like a cosmic slingshot, the black hole wasn't just consuming matter, it was converting some into raw energy and hurling it back into space. The numbers lined up perfectly with predictions: too massive to be a neutron star, too dark to be anything else. Even skeptics like Hawking had to concede nature had handed us a textbook black hole, complete with all the ghastly bells and whistles. What makes Cygnus X-1 so extraordinary isn't just its confirmation of Einstein's equations. It's how mundane it turned out to be. This wasn't some rare cosmic fluke, it was a blueprint. Suddenly, astronomers realized black holes weren't just lurking in the shadows, they were out there, feasting on stars, shaping galaxies, and rewriting the rules right under our noses. Cygnus didn't just prove black holes existed, it proved the universe was teeming with them. Even geniuses love a good gamble, and Stephen Hawking was no exception. In 1974, at the peak of the Cygnus X-1 debate, he made a bet that would become legendary not for the stakes, but for what it revealed about science itself. His wager with fellow physicist Kip Thorne wasn't about money or pride. It was a playful clash of intuition versus hard evidence. Hawking, ever the skeptic, bet a year's subscription to Penthouse magazine that Cygnus X-1 wasn't a black hole. Thorne, confident in the data, took the opposite side. On the surface, it was a cheeky bet between colleagues, but underneath, a brilliant dramatization of how science really works, not as a parade of unshakable truths, but as a series of educated guesses, rival theories, and yes, even friendly disagreements. Hawking's hesitation wasn't just stubbornness. At the time, the idea of black holes still felt like science fiction to many, even those who studied them. The math said they should exist, but nature had a habit of throwing curveballs. What if Cygnus X-1 was something even stranger, a neutron star with quirks nobody had predicted? Or an entirely new class of object? Hawking later admitted he bet against black holes partly as insurance. If he was wrong, he'd at least have the consolation of groundbreaking discovery. If he was right, well, that would have rewritten astrophysics. The bet dragged on for years as astronomers piled up evidence. With every new observation of Cygnus X-1's voracious appetite, Thorne's confidence grew. Hawking, ever the showman, eventually conceded in the most public way possible. During a lecture in 1990, he literally rolled onto stage in his wheelchair, reached into a bag, and presented Thorne with an adult magazine, paid for, of course, by his loss. The crowd erupted in laughter, but the moment held deeper significance. Here was one of history's greatest minds, cheerfully admitting he'd been outplayed by the universe. That's the real lesson of the bet. Science isn't about being right from the start. It's about having the courage to be proven wrong. Hawking's willingness to lose gracefully showcased the humility at the heart of discovery. And in the end, the joke was on him. Cygnus X-1 didn't just confirm black holes were real. It proved they could be found in our cosmic backyard, lurking in the darkness, waiting to upend everything we thought we knew. Decades of painstaking observation turned Cygnus X-1 from a cosmic curiosity into a landmark discovery. The key to unlocking its secret lay not in one eureka moment, but in a slow accumulation of evidence, like assembling a puzzle where every piece defied conventional astronomy. X-ray satellites like Uhuru in the 1970s played detective, capturing the violent flickers of matter spiraling into oblivion. Each burst of radiation told a story, gas ripped from its stellar companion, heated to millions of degrees and vanishing into darkness with clockwork regularity. Radio telescopes added another layer to the mystery. They revealed twin jets of particles screaming outward at nearly light speed, a telltale sign of a black hole's ferocious energy conversion. Unlike neutron stars, which emit steady pulses, Cygnus X-1's output was chaotic, unpredictable, as if nature itself was struggling to process the violence unfolding. Then came the clinching detail, precise measurements of the supergiant star's wobble. Its rhythmic sway betrayed the presence of an invisible object so massive, so compact, that no known phenomenon, not a neutron star, not a white dwarf, could explain it. The math was unforgiving. 8 solar masses crammed into a space smaller than Manhattan. But science demands more than just numbers. It requires consensus, and that's where decades of debate paid off. Skeptics pointed to alternative theories, maybe an exotic quark star, or a neutron star shrouded in unprecedented ways. One by one, these possibilities crumbled under scrutiny. By the 1990s, even the holdouts conceded. Advanced instruments like the Chandra X-ray Observatory mapped the accretion disk's furious whirlpool in stunning detail, while Hubble observations pinned down the system's distance and mass with razor precision. The verdict was inescapable. Cygnus X-1 wasn't just a black hole. It was a Rosetta Stone, proving that Einstein's wildest equations weren't abstractions. They were blueprints for monsters hiding in plain sight. What makes this confirmation so extraordinary isn't just the triumph of theory over doubt. It's the humility it imposed on science. Here was an object so extreme, it stretched our tools and imaginations to their limits. And in the end, the universe didn't bend to our expectations. We had to bend to its reality. Cygnus X-1 didn't just change textbooks. It rewrote our cosmic address, reminding us that the night sky isn't just a tapestry of stars. It's a graveyard of giants where darkness hums with the echoes of everything it's consumed. Cygnus X-1 isn't just any black hole, it's a heavyweight champion of the cosmos. Tipping the scales at 21 times the mass of our Sun, this behemoth defies expectations, lurking 6,000 light-years away in the constellation Cygnus. To grasp its sheer scale, picture squeezing over 20 suns into a space no wider than a city. The result, a gravitational monster so dense, it warps the very fabric of space-time around it. But the real spectacle isn't the black hole itself, it's the frenzied chaos it creates. Cygnus X-1 isn't dining alone. It's locked in a lethal tango with a blue supergiant star, designated HD 226868. Every 5.6 days, the pair completes a dizzying orbit, their dance floor a blistering stage of violence. The supergiant's outer layers, whipped away by the black hole's gravity, spiral inward at nearly light speed, forming a superheated accretion disk. Imagine a whirlpool of plasma glowing at millions of degrees and stretching across millions of miles, its inner edges vanishing into darkness as matter crosses the event horizon. What makes this disk so mesmerizing is its turbulence. X-ray telescopes reveal flickers and flares, the telltale signs of gas being shredded and compressed. Some of that material doesn't fall in quietly. It's catapulted outward in colossal jets, shooting particles at relativistic speeds. These jets, visible in radio waves, stretch light years into space, a testament to the black hole's ability to turn destruction into creation. Yet Cygnus X-1 holds another surprise. It's spinning. Measurements suggest this cosmic giant rotates at over 90% of the maximum speed allowed by physics, dragging space-time around it like a whirlpool. That spin isn't just a quirky detail. It powers the black hole's particle jets and shapes how it consumes its stellar companion. At 6,000 light-years away, Cygnus X-1 feels distant, but in cosmic terms, it's practically next door. Its proximity offers astronomers a front-row seat to the brutal elegance of black hole physics, a reminder that the universe's most extreme phenomena aren't just theoretical. They're out there, shaping the night sky one cataclysmic bite at a time. Cygnus X-1 may have stolen the spotlight, but it wasn't the only cosmic oddball making waves in the early days of black hole hunting. Take SS433, for instance, a bizarre object in the constellation Aquila that had astronomers scratching their heads in the 1970s. This thing didn't just emit X-rays, it fired off twin jets of plasma at a quarter the speed of light, twisting and precessing like a spinning top gone rogue. At first glance, it seemed like prime black hole material, but the closer scientists looked, the murkier things got. Its emissions wobbled with a precise 162-day cycle, hinting at an accretion disk tilted like a wobbling dinner plate. The kicker, unlike Cygnus X-1, SS433's central object was too lightweight, likely a neutron star, not a black hole. Still, its antics forced researchers to grapple with how extreme physics could bend the rules, proving the universe had plenty of ways to mimic a black hole without actually being one. Then there's LMC X3, lurking in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Discovered in the same era as Cygnus X-1, this X-ray source had all the hallmarks of a black hole candidate: violent bursts of radiation, a massive unseen companion, and an accretion disk hotter than the core of a star. But LMC X3 had a credibility problem: distance. Sitting 160,000 light-years away, it was far harder to study in detail than Cygnus. Without precise measurements of its companion star's wobble or mass, astronomers couldn't rule out alternative explanations, like an unusually beefy neutron star. It wasn't until decades later, with sharper telescopes, that LMC X3's black hole status solidified, long after Cygnus had already rewritten the textbooks. What's fascinating about these also-rans isn't just their near-miss fame. They reveal how messy scientific discovery really is. For every Cygnus X-1, a clean, textbook case, there are a dozen cosmic riddles like SS433, blurring the line between black holes and their exotic cousins. These objects challenged researchers to refine their tools, question assumptions, and admit that nature rarely fits neat categories. In the end, being first wasn't just about having the right properties, it was about leaving no room for doubt. Cygnus X-1 crossed that threshold, the others paved the way. While Cygnus X-1 proved black holes could form from dying stars, there's another, far stranger possibility lurking in the shadows of cosmic history. Black holes born not from stellar collapse, but from the raw chaos of the universe's infancy. These are primordial black holes, hypothetical relics that might have formed microseconds after the Big Bang, when the cosmos was a seething, ultra-dense soup of energy. Unlike their stellar mass cousins, these wouldn't need a star's death to exist. They'd be cosmic artifacts forged in the furnace of creation itself. Picture the early universe not as the vast expanse we know today, but as a roiling plasma where density fluctuated wildly. In some regions, matter might have been packed so tightly that gravity overpowered everything else, collapsing pockets of space into black holes with masses ranging from a speck of dust to 1,000 suns. Unlike the black holes we've detected, which announce their presence by devouring nearby matter, primordial black holes could be drifting silently through space, dark, ancient, and nearly impossible to spot. Why haven't we found them yet? Part of the challenge is their potential size. A primordial black hole with the mass of an asteroid could be as small as a single atom, making it effectively invisible unless it passed right in front of a star, bending its light like a cosmic magnifying glass. Some might have already evaporated entirely, thanks to Hawking radiation, a slow leak of energy predicted to shrink tiny black holes over billions of years. Others could be hiding in plain sight, masquerading as dark matter, the elusive substance that makes up most of the universe's mass but refuses to interact with light. The hunt for these relics isn't just academic. If they exist, primordial black holes could solve some of astrophysics' biggest mysteries. Their gravity might explain odd gravitational lensing events where distant stars flicker unexpectedly. They could account for rogue planet mass objects floating untethered to any star. Some theorists even suggest they might have seeded the supermassive black holes that now lurk at the centers of galaxies, growing over eons from tiny seeds sown in the universe's first moments. Yet for all their promise, primordial black holes remain ghosts in the cosmic machine. Telescopes scan for telltale flashes of their passage, while physicists sift through data from gravitational wave detectors, hoping for a whisper of their collisions. The irony is delicious. The very black holes that might be everywhere could also be nowhere, a reminder that the universe still holds cards close to its chest. Whether they are out there or not, the search reshapes our understanding of reality, proving that sometimes the most profound discoveries begin with a simple question: what if the darkness hides more than we ever dared to guess? Cygnus X-1 may be a cosmic heavyweight, but it's a featherweight compared to the true titans lurking at the hearts of galaxies. While stellar black holes like Cygnus form from the collapse of a single massive star, their supermassive cousins, like Sagittarius, at the center of our Milky Way, operate on a scale that defies comprehension. Think of it like comparing a campfire to a volcanic eruption. Both involve heat and light, but the forces at play are worlds apart. Take size first. Cygnus X-1 packs the mass of 21 suns into a space smaller than New York City. Sagittarius A, it's a behemoth weighing 4 million solar masses crammed into a volume that could fit within the orbit of Mercury. That's not just bigger, it's a difference of cosmic proportion. If Cygnus X-1's gravity is a firm handshake, Sagittarius A's grip could crush an entire solar system without breaking a sweat. Their origins are just as distinct. Stellar black holes are born from catastrophic violence, the explosive death throes of a massive star going supernova. But supermassive black holes, their birth remains one of astronomy's great mysteries. They might have started as smaller black holes that merged and grew, swallowing gas, stars, and even other black holes over billions of years. Or perhaps they formed directly from collapsing gas clouds in the early universe, bypassing the stellar stage entirely. Some might even owe their existence to those hypothetical primordial black holes, seeding their growth in the cosmic dawn. The way they behave tells two different stories, too. Cygnus X-1 feasts on its stellar companion in a relatively orderly fashion. Its accretion disk glowing fiercely in X-rays. Sagittarius A, by contrast, is a more capricious diner. Though mostly quiet now, it occasionally flares up, devouring whole stars or gas clouds with bursts of energy that light up the galactic center. Yet despite its size, it's oddly subdued, like a sleeping giant that occasionally stirs, reminding the Milky Way who's in charge. And then there's influence. A stellar black hole might shape its immediate surroundings, warping nearby space and birthing X-ray jets. But a supermassive black hole, it's the gravitational anchor of an entire galaxy. Stars whip around Sagittarius at thousands of miles per second, their orbits tracing the invisible hand of its gravity. Some scientists believe these monsters don't just live in galaxies, they shape them, regulating star formation and galactic evolution in ways we're only beginning to understand. Yet for all their differences, both types share one haunting trait, an event horizon, the ultimate point of no return. Whether it's the modest boundary of Cygnus X-1 or the vast, silent maw of Sagittarius A, crossing that threshold means vanishing from the universe as we know it. It's a reminder that black holes, no matter their size, are nature's great equalizers, where the rules of physics as we know them cease to apply and darkness becomes the final answer. Before Uhuru launched into orbit in 1970, black holes were little more than theoretical phantoms, mathematical shadows that might or might not exist. But everything changed when this small, unassuming satellite opened its X-ray eyes to the cosmos. Imagine trying to study a pitch-black room with only a flashlight. That's what optical astronomy was like before X-ray telescopes. Black holes don't emit visible light, but their gravitational frenzy creates something just as telling: superheated plasma, swirling at nearly light speed and glowing fiercely in X-rays. Uhuru, Swahili for freedom, didn't just flick that switch, it rewired our entire understanding of the invisible universe. The genius of X-ray astronomy lies in its focus on violence. In space, X-rays don't come from gentle processes. They're the death cries of matter pushed to extremes, whether by exploding stars, colliding neutron stars, or the gravitational meat grinders around black holes. When gas spirals into an accretion disk, friction heats it to millions of degrees, stripping electrons from atoms and sending X-rays screaming across the cosmos. Uhuru's instruments were fine-tuned to catch these screams, mapping sources like Cygnus X-1 with unprecedented precision. Suddenly, astronomers had a way to see black holes not by their absence of light, but by the blistering fury they inflicted on everything that wandered too close. But here's what made Uhuru revolutionary. It didn't just spot X-rays, it decoded their patterns. The flickering emissions from Cygnus X-1 weren't random. They pulsed hundreds of times per second, a staccato beat betraying the frantic churn of matter at the brink of oblivion. That rhythm became a smoking gun. Only an object with a black hole's crushing gravity could whip gas into such frenzied, high-energy dances. Optical telescopes saw a calm blue supergiant. Uhuru revealed its invisible partner tearing strips off it, a cosmic vampire glowing in X-rays. Later missions like Chandra and XMM Newton built on Uhuru's legacy, zooming in with resolutions sharp enough to trace the accretion disk structure, how it warps, how it flares, even how it occasionally hiccups when a particularly large clump of matter plunges in. Without these X-ray eyes, black holes might have remained ghostly hypotheticals. Instead, we now know they're not rare anomalies but cornerstones of the cosmos, shaping galaxies and devouring stars with terrifying regularity. Uhuru's quiet observations didn't just confirm Einstein's wildest ideas. They gave us front-row seats to the universe's most spectacular demolition derby. To understand how a cosmic monster like Cygnus X-1 came to be, we need to witness the death of a star, not just any star, but one of the universe's true giants. Picture a celestial titan 20 times more massive than our sun, burning through its fuel at a furious pace. For millions of years, it shines brilliantly, fusing hydrogen into helium, then helium into carbon, and so on, each layer of its core collapsing inward as it exhausts one element after another. This relentless cycle can't last forever. Unlike smaller stars that fade gently into white dwarfs, this behemoth is destined for something far more spectacular and cataclysmic. When such a star finally runs out of fusible material, the delicate balance between gravity and radiation tips catastrophically. For eons, the outward pressure of nuclear fusion held gravity at bay, but now, with no energy left to push back, gravity wins in an instant. The core collapses not slowly, but in a fraction of a second, hurtling inward at nearly a quarter the speed of light. The outer layers, suddenly without support, come crashing down like a building whose foundation has vanished. The result, a supernova explosion so violent it can outshine entire galaxies for weeks, scattering star stuff across the cosmos. But the fireworks aren't the real story. What happens next is even more extraordinary. If the collapsing core is between about 3 and 20 solar masses, it doesn't stop at forming a neutron star, it keeps going. Atoms themselves disintegrate under the crush of gravity, protons and electrons merging into neutrons until even those can't hold the line. The collapse continues until all that mass is squeezed into a singularity, a point of infinite density where space and time cease to behave as we know them. Around it forms the event horizon, a spherical boundary from which nothing, not even light, can escape. A black hole is born. This is almost certainly the origin story of Cygnus X-1. Millions of years ago, in what we now call the constellation Cygnus, a massive star met its violent end. The supernova would have been visible from Earth had there been anyone to see it, a sudden, brilliant new star in the sky before fading into darkness. What remained was the black hole we detect today, along with its stellar companion, the blue supergiant HD 226868. That star, remarkably, survived the explosion, likely because it orbited just far enough away to avoid being obliterated by the blast. Now it serves as both witness and unwilling participant in the black hole's relentless feast. But here's where the plot thickens. Not every massive star becomes a black hole. The fate of a dying star depends on a delicate interplay of mass, rotation, and even chemistry. Stars with slightly less mass might end up as neutron stars, their collapse halted by quantum forces. Others, born in binary systems like Cygnus X-1, can have their destinies altered by stellar companions stealing their outer layers before death. Even the star's metallicity, the amount of elements heavier than hydrogen and helium it contains, plays a role. More metals mean stronger stellar winds during its life, which can strip away mass and leave a smaller core behind. The birth of a black hole isn't just a one-time event, it's a process that shapes its surroundings for eons. The supernova explosion enriches the galaxy with heavy elements, the raw materials for future stars and planets. The black hole itself, though invisible, announces its presence through its gravitational influence and the high-energy emissions of its accretion disk. Cygnus X-1's violent birth wasn't an ending. It was the opening act of a cosmic drama that's still unfolding, one that taught us how stars die, how black holes awaken, and how the universe constantly reinvents itself in the most spectacular ways imaginable. When Cygnus X-1 burst onto the scientific scene, it didn't just revolutionize astronomy, it ignited the collective imagination. Here was something straight out of science fiction, but with hard evidence to back it up, a cosmic abyss so powerful it twisted the laws of physics. Unsurprisingly, artists and storytellers seized on its mystique, weaving it into music, films, and literature that resonated far beyond academic circles. Take Rush's 1977 concept album Cygnus X-1, a prog rock epic that transformed the black hole into a metaphor for existential adventure. The album's protagonist, a space traveler, plunges into the void, only to emerge transformed, mirroring humanity's own journey from fear to fascination. Hollywood, never one to miss a cosmic trend, quickly followed suit. Black holes became shorthand for the ultimate unknown, appearing in films like The Black Hole 1979 and later Interstellar 2014, where they served as portals to alternate dimensions and time-bending paradoxes. While these depictions often took creative liberties, spaghettification isn't quite as photogenic as Hollywood suggests. They captured the eerie allure of these gravitational monsters. Even Star Trek and Doctor Who couldn't resist, scripting black holes as gateways to parallel universes or traps for ancient alien civilizations. But the cultural impact wasn't just about spectacle. Cygnus X-1 made black holes relatable. Before its discovery, they were abstract equations. Afterward, they became characters in humanity's story. Sci-fi authors like Arthur C. Clarke and Larry Niven used them as backdrops for philosophical dilemmas. What happens to identity in a place where time stops? Could a black hole be a tool, a prison, or even a god? Meanwhile, documentaries and planetarium shows turned accretion disks into swirling visual poetry, making cosmic violence oddly beautiful, perhaps the most telling sign of Cygnus X-1's grip on culture. It blurred the line between science and myth. Ancient civilizations had their celestial monsters, dragons that eclipsed the sun, serpents that devoured the moon. Cygnus X-1 became ours, a real-life cosmic predator, lurking in the data of telescopes and the lyrics of rock songs. It proved that the universe could still deliver mysteries grand enough to spark both equations and electric guitar solos. And in doing so, it turned all of us into stargazers, peering into the dark and wondering what else might be out there. The discovery of Cygnus X-1 was just the beginning, a crack in the cosmic dam that unleashed a flood of black hole revelations. Fast forward to the 21st century, and the tools we use to hunt these gravitational beasts have evolved beyond X-ray telescopes. In 2015, a century after Einstein predicted their existence, humanity detected gravitational waves for the first time, ripples in space-time caused by the violent merger of two black holes over 1 billion light-years away. The Laser Interferometer Gravitational Wave Observatory, or LIGO, didn't just hear the universe's soundtrack, it opened a whole new window into the invisible. Those first detected waves came from a collision between black holes 29 and 36 times the mass of our Sun, far larger than Cygnus X-1. Unlike X-ray observations, which rely on matter screaming as it falls into a black hole, gravitational waves capture the raw choreography of space-time itself twisting under extreme gravity. The signal lasted just 0.2 of a second, but it revolutionized astrophysics. Suddenly, we could study black holes even when they weren't actively feeding, when they floated in darkness, invisible to traditional telescopes. Then came the Event Horizon Telescope's triumph in 2019. This globe-spanning network of radio telescopes pieced together the first ever image of a black hole's shadow, the supermassive monster at the heart of galaxy M87. The iconic orange ring, glowing with light bent by unimaginable gravity, wasn't just a photo. It was proof that black holes aren't theoretical abstractions, but tangible cosmic structures with measurable shapes and sizes. The image matched Einstein's equations with eerie precision, confirming that even a century later, his math still holds up under the most extreme conditions. Meanwhile, discoveries kept piling up. Astronomers found intermediate mass black holes, the elusive, missing link between stellar black holes like Cygnus X-1 and supermassive giants. Some lurk in dense star clusters, others revealed themselves by tearing apart wayward stars in spectacular tidal disruption events. Then there's the growing mystery of rogue black holes drifting through galaxies alone, detectable only by the way their gravity lenses light from distant stars. Perhaps the strangest twist came with the realization that black holes might not be the ultimate in points we once thought. Hawking radiation, the theoretical process by which black holes slowly evaporate, suggests they could vanish entirely over trillions of years. It's a humbling thought. Even the universe's most indomitable monsters might someday fade to nothing. From Cygnus X-1's smoking gun to today's multi-messenger astronomy, each discovery peels back another layer of the black hole enigma. We've gone from doubting their existence to mapping their shadows, from betting against them to using them as cosmic laboratories, and the wildest part: we're just getting started. When NASA launched the Chandra X-ray Observatory in 1999, it didn't just send another telescope into orbit, it unleashed a detective capable of seeing the universe's most violent scenes in razor-sharp detail. For an enigma like Cygnus X-1, Chandra was game-changing. Where earlier X-ray telescopes saw blurry hotspots, Chandra's precision revealed the black hole's secrets down to the atomic level, like swapping a candle for a spotlight in a cosmic crime scene. One of its first breakthroughs was measuring Cygnus X-1's spin, an astonishing feat considering black holes have no solid surface to track. Instead, Chandra analyzed the distortion of X-rays emitted by the accretion disk. The results were staggering. This cosmic monster rotates at over 90% of the maximum speed allowed by physics. Picture a whirlpool where space-time itself is dragged around so violently that even light struggles to escape the vortex. That spin isn't just for show. It powers the black hole's relativistic jets, those infamous particle beams screaming outward at nearly light speed. Chandra's observations showed these jets weren't steady streams but chaotic geysers, flickering as magnetic fields near the event horizon twisted and snapped like rubber bands under tension. But Chandra didn't stop there. It mapped the disk's temperature gradient with precision, revealing how gas heats up to millions of degrees as it spirals inward, emitting X-rays like a cosmic siren call. Occasionally, the telescope caught flares, violent bursts of energy as chunks of the supergiant star's stolen atmosphere plunged toward oblivion. These weren't just random bursts, they followed patterns, clues to how turbulence and magnetic fields choreograph matter's final moments before crossing the event horizon. Perhaps most crucially, Chandra helped nail down Cygnus X-1's distance and mass once and for all. By combining X-ray data with optical observations of its companion star, astronomers confirmed the black hole's 21 solar mass heft, making it the heaviest stellar mass black hole known at the time. The implications rippled through astrophysics. If stars could collapse into objects this massive, it meant our models of stellar evolution needed tweaking. What makes Chandra's contribution so monumental isn't just the data, it's the perspective shift. Before, Cygnus X-1 was a fascinating oddity. After, it became a laboratory. Scientists could test theories about how black holes warp space, accelerate particles, and even how their spin might one day offer clues about the universe's expansion. Chandra turned a distant curiosity into a touchstone, proving that even the darkest corners of the cosmos can't hide from the right tools, or humanity's relentless curiosity. Right now, the blue supergiant companion to Cygnus X-1 is locked in a cosmic dance with death, but how long before gravity calls the final tune? This isn't just academic curiosity, it's a glimpse into the future of one of the most famous binary systems in the universe. The supergiant HD 226868 is no lightweight itself, weighing in at around 40 solar masses. It's a ticking time bomb. Stars this massive live fast and die violently, burning through their fuel in just a few million years. When its core finally exhausts its nuclear fuel, the collapse could trigger another supernova, potentially leaving behind a second black hole. Imagine it. Two gravitational monsters circling each other in a slow, silent waltz, their orbits tightening over millennia until someday they merge in a cataclysm that shakes the fabric of space-time itself. But here's where the mystery deepens. Not all massive stars become black holes. Some explode so fiercely they leave nothing behind. The outcome hinges on delicate factors: how much mass the star sheds in violent stellar winds before death, whether it's been peeled back by its black hole companion, even the mix of heavy elements in its core. Current models suggest HD 226868 is right on the edge. If it loses enough mass before collapsing, it might end up as a neutron star, a dense remnant, yes, but not quite a black hole. If it holds onto more of its bulk, gravity could win, squeezing it into another singularity. Astronomers are watching closely because the answer could rewrite our understanding of how binary black holes form. And then there's the wild card. What if the supergiant's death kick sends the newborn black hole hurtling away? Supernova aren't gentle. They can eject stellar remnants at incredible speeds. If the explosion isn't perfectly symmetrical, the recoil might fling the second black hole out of the system entirely, leaving Cygnus X-1 alone in the void. Alternatively, the two could remain bound, spiraling closer until gravitational waves bleed off their orbital energy. Simulations suggest that in a few million years, a blink in cosmic time, their dance could end in a collision, sending ripples through the universe detectable by observatories like LIGO. The real tantalizing question isn't just what happens to this star, it's how many systems like this exist. Cygnus X-1 might be the first black hole we found, but it's likely not the only one dining on a supergiant companion. Across the Milky Way, other binaries could be hiding similar fates, their stories playing out in X-ray flickers and radio whispers. Each one is a natural laboratory, testing our theories about stellar evolution, gravity, and the violent births of cosmic monsters. Every observation of Cygnus X-1's companion isn't just about one star's fate. It's a preview of the universe's grand, unrelenting cycle of destruction and rebirth. And somewhere in that cycle, the answers to our biggest questions might be waiting. The story of Cygnus X-1 took center stage once again in 2020, when the Nobel Prize in Physics honored breakthroughs that trace their lineage directly back to this cosmic pioneer. The prize was split between Roger Penrose, who mathematically proved black holes could exist under Einstein's theory, and Reinhard Genzel and Andrea Ghez, whose teams independently confirmed a supermassive black hole lurks at our galaxy's heart. But here's where Cygnus X-1 quietly flexes its legacy. It was the first real-world evidence that Penrose's equations weren't just elegant math, but descriptions of actual cosmic beasts. Without those early X-ray whispers from Cygnus, the Nobel-winning work might have remained theoretical for decades longer. Penrose's contributions in the 1960s showed how black holes could form from collapsing stars, complete with their eerie singularities and event horizons. At the time, even his peers dismissed it as mathematical fantasy. Then came Cygnus X-1 in '71, a living, breathing validation of his calculations. Suddenly, Penrose's abstract trapped surfaces and cosmic censorship hypotheses weren't just chalkboard curiosities. They were stamped across the sky in X-ray flares and gravitational wobbles. Genzel and Gez's later work, meticulously tracking stars orbiting an invisible monster at the Milky Way's core, followed the same playbook Cygnus pioneered. Watch how visible objects dance with the invisible and let gravity spill the secrets. What's striking is how these Nobel breakthroughs bookend the black hole saga. Penrose gave us the theoretical foundation, Cygnus X-1 offered the first concrete proof, and Genzel and Ghez revealed that these monsters aren't just outliers, they're galactic architects shaping the universe from the shadows. The Nobel Committee didn't just reward isolated discoveries, they honored a century-long chain reaction of curiosity, where each breakthrough built on the last. And right there in the middle, quietly anchoring it all, was that unassuming X-ray source in Cygnus, the first crack in the dam that let the flood of black hole science pour through. Yet the prize also hints at how much we've yet to learn. Penrose's work on singularities clashes with quantum mechanics. Genzel and Gez's black hole is weirdly quiet compared to predictions, and Cygnus X-1 still surprises us, like when recent measurements showed it's farther away and thus more massive than we'd thought. The Nobel didn't close the book on black holes, it underlined how many pages remain unturned. And somewhere in those unwritten chapters, Cygnus X-1's descendants, the black holes we've yet to find, are waiting to rewrite the story once more. The hunt for black holes is about to leap into hyperspace, thanks to a new generation of telescopes and detectors designed to peel back cosmic history like never before. Leading the charge is LISA, the Laser Interferometer Space Antenna, a revolutionary mission set to launch in the 2030s. Unlike ground-based observatories like LIGO, LISA will float in space as a trio of satellites spanning millions of miles, connected by lasers so precise they can detect gravitational waves from mergers that happened when the universe was in its infancy. Picture it, a web of light straining to catch whispers from the dawn of time when the first black holes may have formed. These primordial giants, if they exist, could reveal whether black holes helped seed the very first galaxies, their gravity acting as invisible scaffolding for stars to gather around. Then there's the James Webb Space Telescope, already rewriting the rules of cosmic observation. While it wasn't designed specifically to hunt black holes, its infrared eyes are uncovering quasars, supermassive black holes feeding furiously, so distant that their light has traveled nearly 13 billion years to reach us. These aren't just ancient black holes, they're cosmic conundrums. How did they grow so massive so quickly after the Big Bang? Some theories suggest they started as direct collapse black holes, skipping the star phase entirely by condensing straight from giant gas clouds. Others speculate they're the remnants of even earlier black holes, colliding and merging in a frenzy of growth. Webb's observations are forcing us to rethink the timeline of cosmic history, proving that black holes weren't just spectators in the early universe, they were architects. But the real game changer might come from pulsar timing arrays, networks of radio telescopes tracking the faint hiccups of spinning neutron stars. These cosmic metronomes are so precise that passing gravitational waves, like those from supermassive black hole binaries, tweak their rhythms ever so slightly. If successful, these arrays could map the gravitational wave background of the universe, a faint hum from countless black hole mergers across cosmic time. It's like tuning into a radio station that plays nothing but the echoes of colliding giants, a symphony of space-time ripples telling stories we've never heard before. What ties these missions together is their ability to probe the dark age of black holes, the era before stars and galaxies lit up the cosmos. If primordial black holes exist, LISA might catch their mergers, Webb could spot their influence on early gas clouds, and pulsar arrays might hear their cumulative whispers. Each tool offers a different lens, and together they could solve mysteries that have lingered since Cygnus X-1 first cracked open the door. Are black holes older than stars? Did they shape the universe's structure? The answers aren't just buried in the math anymore, they're out there, waiting for the right instrument to listen. The universe might have hidden its very first black hole, not among the swirling galaxies we see today, but buried deep in the cosmic dawn, a relic from when the cosmos was just taking shape. This isn't science fiction, it's a tantalizing possibility that physicists call a primordial black hole. A hypothetical monster born not from a dying star, but from the raw turbulence of the Big Bang itself. Picture the infant universe, a seething cauldron of energy where density fluctuations could have been extreme enough for pockets of space to collapse directly into black holes. Some might have been as light as a penny, others heavier than 1,000 suns, all forged in the first second of existence, lurking unseen for billions of years. How would we even begin to hunt such an ancient phantom? Unlike stellar black holes like Cygnus X-1, which announce themselves by devouring nearby stars, primordial black holes could be drifting silently through the cosmos, invisible unless they pass in front of a distant star. Their gravity would bend the starlight like a lens, creating a brief but telltale brightening, a phenomenon astronomers already use to spot rogue planets. Telescopes like the upcoming Nancy Grace Roman Space Telescope are designed to scan for these microlensing events, sifting through millions of stars for the subtle flicker of a black hole's passage. But there's another, more dramatic way these relics might betray their presence: by exploding. Stephen Hawking theorized that black holes slowly leak energy, a process now called Hawking radiation. For massive black holes, this trickle is negligible, but tiny ones could evaporate completely in a burst of gamma rays. Satellite arrays scanning for gamma ray bursts have occasionally detected unexplained flashes with no accompanying supernova. Could these be the death throes of primordial black holes formed at the beginning of time? The implications stretch beyond curiosity. If primordial black holes exist, they could solve one of astronomy's greatest mysteries: dark matter. Though invisible, dark matter's gravitational pull shapes galaxies, and some theories suggest it might be composed entirely of these ancient black holes. Others speculate they could have acted as seeds for the supermassive black holes now found at galactic centers, growing over eons by swallowing gas and stars. Yet the search is fraught with challenges. Primordial black holes could be anywhere floating between stars, hiding in the halos of galaxies, even passing through our solar system unnoticed. Their predicted masses span 60 orders of magnitude from subatomic to supermassive, making them a cosmic needle in a haystack, and if they're too small, they may have already evaporated, leaving no trace. The hunt for the universe's first black hole isn't just about adding another entry to the cosmic catalogue. It's a quest to rewrite our understanding of the Big Bang, dark matter, and the very fabric of space-time. Whether they're out there or not, the search forces us to confront the deepest questions about how the universe began, what it's made of, and what other secrets might be hiding in the darkness. Cygnus X-1 didn't just change textbooks, it rewrote how we teach the cosmos. Before its discovery, black holes were relegated to the final chapters of astrophysics courses, presented as speculative curiosities wrapped in dense equations. But the moment Cygnus X-1 transitioned from theory to reality, it became the ultimate classroom case study. Professors could point to actual data, X-ray flares, orbital wobbles, relativistic jets, and say, this isn't just math. It's out there, right now, devouring a star. Suddenly, abstract concepts like event horizons and singularities had a tangible anchor, a celestial lab experiment unfolding in real time. The impact rippled beyond university halls. Science museums built entire exhibits around Cygnus X-1, using interactive models to simulate its gravitational whirlpool. Planetarium shows projected its accretion disk in domed glory, turning complex physics into visceral spectacle. Even high school curricula evolved, with teachers using Cygnus as a gateway to discuss stellar evolution, Einstein's relativity, and the scientific method itself. Here was a mystery solved not by accident, but through decades of incremental evidence, a masterclass in how science works when curiosity meets rigor. Perhaps its most profound legacy lies in the careers it sparked. Countless astronomers first felt the thrill of discovery through Cygnus X-1's story, from the audacity of John Michell's 18th century dark stars to the tension of Hawking's bet. For aspiring scientists, it became a symbol of how patience and collaboration can peel back the universe's deepest secrets. The black hole's journey from heresy to fact mirrors science's own, messy, contentious, and ultimately triumphant. Yet Cygnus X-1's educational power isn't just about what we've learned, it's about what we're still figuring out. Every new observation, from Chandra's spin measurements to debated distance recalculations, reinforces a critical lesson. Even textbook facts remain open to revision. That humility, the awareness that today's cornerstone could be tomorrow's stepping stone, is Cygnus X-1's greatest gift to the next generation of cosmic explorers. Here's something to chew on. If you stumbled upon a brand new black hole and got to slap a name on it, what would you choose? Seriously, think about it. Astronomers have already given us gems like the unicorn for a tiny black hole, or pauehi, a Hawaiian phrase meaning embellished dark source of unending creation. But what's your take? Maybe something mythological like Kronos after the Titan who devoured his children, fitting for a cosmic vacuum cleaner. Or perhaps you'd go playful, dubbing it the Cookie Monster for its endless appetite. Names aren't just labels, they shape how we see these cosmic beasts. Calling one the Darkness Engine paints a different picture than the Gravity Well. And let's not forget pop culture. Would Darth Void make you take black holes more seriously or just crack you up? Drop your ideas in the comments, whether poetic, eerie, or downright silly, because who knows? The next black hole discovery might just need a name, and yours could stick. After all, Cygnus X-1 didn't start as a household name, it earned its fame. Now it's your turn to imagine what's lurking out there, waiting for the perfect title. Cygnus X-1 wasn't just a scientific breakthrough, it was a revolution wrapped in X-rays and starlight. Think about it, for centuries, black holes existed only as scribbles in notebooks, equations that even Einstein doubted could be real. Then along came this unassuming patch of sky in the constellation Cygnus, whispering secrets through flickering radiation. The data didn't just confirm a theory, it tore open an entirely new chapter in astronomy, proving the universe was stranger, more violent, and more magnificent than we'd ever dreamed. Look how far we've come since then. That first grainy X-ray signature has blossomed into an entire field of discovery. We've snapped photos of black hole shadows, eavesdropped on their collisions through gravitational waves, and even caught them flaring in the hearts of distant galaxies. Cygnus X-1 was the gateway, the first domino that set off a chain reaction of cosmic exploration. Without it, we might still be debating whether black holes existed at all, let alone unraveling their role as galactic architects and time warps. But here's the real magic: the story isn't over. Every time we think we've got black holes figured out, they surprise us. Cygnus X-1 itself still defies expectations. Recent measurements showed it's heavier and farther away than we thought, forcing us to rethink how these monsters form. And with next-gen telescopes like LISA and the Roman Space Telescope coming online, who knows what else is lurking in the dark? Maybe primordial black holes from the dawn of time. Maybe wormholes or new layers to Einstein's relativity we've yet to crack. That's the beauty of cosmos. It's always one step ahead, dangling mysteries just beyond our reach. Cygnus X-1 taught us that the universe doesn't give up its secrets easily, but that's what makes the hunt so thrilling. So stay curious, keep looking up, and remember, every time we peer into the void, it peers back, ready to reveal something new. The first black hole was just the beginning.